Hello, I am Dr. Rashid Ahmed from the Department of Physics, and we are at lecture number 9 of the subject of Quantum Mechanics 1. The topic is blackbody radiations. Around 1900, the subject of physics was based upon three well-established theories, that is classical mechanics, classical electrodynamics, and statistical mechanics. But none of them was able to explain the experimental observation related to the blackbody radiations. I will explain later on what this experimental observation was, and hence quantum mechanics took birth out of the necessity to explain that experimental observation. Today we are going to learn that how quantum mechanics could explain something which other three well-established theories could not do so. But let's get started with blackbody and see what actually blackbody is. The blackbody could be any container which is made of any material and placed in the oven, such as this, and we can have a cavity in one of the walls so that radiations can also escape from here. The basic definition of blackbody is that it does not reflect radiations, so all the radiations coming upon it are absorbed and never reflected back. It only absorbs radiation. But can this happen forever? Can blackbody absorb all kind of radiations and never emit? Well, it is not really so, because of the second law of thermodynamics, which says that heat cannot flow from cold body to the hot body. And when this blackbody absorbs all kind of radiations, its environment gets colder than it. So anything other than this blackbody is its environment. And then it is not possible that heat flows from colder environment to the hotter blackbody. So what happens at this moment, that it achieves thermal equilibrium, which means that if the temperature of the blackbody is Tb, so it becomes almost equivalent to the temperature of its environment, which is Te. When this happens, then this blackbody starts emitting the radiations. Here you can see I have shown the visible colors, but these are not the only radiations which blackbody emits. It is a whole spectrum of electromagnetic radiations. So these blackbody radiations are actually electromagnetic radiations. What does this mean, that they are electromagnetic radiations? Actually, electromagnetic radiations are made of two components, that is the electric components, which is from electric field, and magnetic component, which is from the magnetic field, and they are perpendicular to each other. That means that electric field oscillates into the plane and the magnetic field oscillates exactly into the plane which is perpendicular to the electric field, and the radiations move in the direction which is perpendicular to both electric and magnetic field. So the next question is, where do we find such electromagnetic radiations? The answer is everywhere. In our daily life we find electromagnetic radiations everywhere. You can see from the cosmos or from the sun these radiations are coming, and we have the visible range where we can see all colors in the morning. But then we have also the low frequency waves that we call infrared waves and radio waves, and these radio waves are actually used for communications as well. And then we have higher frequencies, that is ultraviolet and X-rays. X-rays are even created artificially, and you see it in your daily life in hospitals for medical purposes. To show you the better diagram, you can see here that we have the electromagnetic radiations of all the wavelengths and related to their uses in our daily life. And one more thing is that the frequency and the wavelength of these radiations are inversely proportional. So when we have higher wavelength, that is longer wavelength, then we have shorter frequency, and we have higher frequency when we have shorter wavelength. So these electromagnetic radiations are part of our daily life, and that's why it's important to study them. But now it's a very important experimental observation and a question which arose around 1900, which these theories, these well-established theories, as I mentioned before, could not explain. So let's move to that and see what this experimental observation was. Once we understand this observation, we will be able to understand that how quantum mechanics could explain that. So the experimental observation was that once we have these radiations coming out of the black body when it is in thermal equilibrium, so how much energy is contained into a single frequency, or in other words we can say that, let's say this is the energy which changes with the nu is the frequency. So this radiant energy distribution or frequency, that how much energy is in this color, so to say, and this is a continuous spectrum going from here to here, including those which are not visible to us. So how much energy is there? To make it even more concrete, I can show you this line where we have divided the frequency into the intervals, and let's say this is a nu frequency and this is nu plus d nu. The question is how much energy is contained in this interval. This is the question. What we expect to be the answer of this question, and that's very straightforward. We expect, before going to this expectation, I show you a mathematical formula for the total energy of mu. You can see that if this is the energy distribution over frequency, which means this is the energy which is in the frequency, if I integrate it from 0 to infinity, I will get the total energy. So this is one fact you have to remember. Now let's come back to our question, that what should one expect about mu, that the distribution of the frequency, distribution of the energy over the frequencies. So our expectation is this straight line, which means that we expect that all the frequencies will take equivalent amount of energy. For example, the energy to this frequency will be equivalent to the energy to this frequency, and energy is equally distributed among all frequencies. Let's say if we change the temperature, let's say if this is for some particular temperature T1, and if we have a lower temperature, the total energy will be decreased, but the straight line will not change, for example for T2. And even if we have higher frequency, a higher temperature than T1, then this line will come here, but still the distribution shall remain the same. And this is a very intuitive answer to the question, that how the energy, radiant energy, is distributed over the frequencies. But does this happen in reality? Well, no. If you do this experimental observation, what you will find is this spectrum, where the intensity or the energy, radiant energy, is distributed over the frequency like this. For example, for the room temperature, you see that the energy distributed over here is very less, and it increases as you go further and further and further, and you reach a peak, and after that peak it decreases again. So this is not a straight line. So if you have a different temperature, if you increase the temperature, the shape of the this curve does not change, although it gets bigger, but it is the same shape. Now to understand this, why is it so, the classical mechanics and classical electrodynamics and statistical mechanics, at that time at 1900, people made many attempts to explain this, and I will discuss one of the attempts, which is called Rayleigh-Jeans approximation. And Rayleigh-Jeans approximated this energy distribution in order to produce the experimental curve. They brought about this formula, this mathematical formula you can see over here. We call that this the energy distributed over the frequency range is called Rayleigh-Jeans, and you can see over here, and this Kb is the Boltzmann constant, whose values is given downstairs there, and T is the temperature, nu is the frequency. So if you plot this against this expected one, let's say this is the experimental observation. This is the experimental observation of the blackbody radiation spectrum, distribution of radiant energy over the frequency. So what happens, that for the lower frequencies it matches the spectrum very well, but when you reach it here, you see that this Rayleigh-Jeans formula goes like in this straight line. So here there are two problems. Problem number one, which is obvious one, that it does not match the experimental line, otherwise it should have came down like this. And the second thing, a serious problem, is what we call the ultraviolet catastrophe, because in here the energy is increasing with the frequency and it goes to infinity, which means that for higher frequencies in this range we will have infinite energy. And if this is radiated out of the black body, then we will actually get ourselves burned if we are sitting near to the black body. So fortunately this doesn't happen. So what we see that the classical mechanics is actually breaking down here. At that time, a German physicist named Planck proposed a very bold idea by saying this, that there is something peculiar inside the black body happening to these radiations, and these radiations are actually not coming out continuously but coming out into the packets of energy. We call it a Planck quantum hypothesis, where it says that the energy is coming out in the packets where h is the Planck constant and nu is the frequency. So this is the packet of energy which is emitted, and then the next packet is emitted, and so on. And this is the value of the Planck constant. And with this hypothesis, Planck was able to devise a new formula called this one here, called the Planck's formula. And you can see that here this term is different, and we have exponential series over here, and we have kBt, same kBt. Now, how does this solve? Well, if you plot this formula, you will get the experimental curve. But how does this solve the problem? For this, we have to see that how much energy a photon can have. Well, the answer is that the energy available, the average of it, the photon will take that energy. In order to understand this, let's go to basics of thermodynamics. Here you can see that if we have a gas, consider that this is a container where we have a gas, and it has three basic parameters, state variables, the pressure, volume, and temperature, and all of these are related by a constant. PV by T is equal to constant. But this constant is not an absolute constant. It depends upon the number of atoms present in this gas. And its value is actually PV by T is equal to N, and N is the number of atoms which are present in this gas, and Kb, as you know, is a Boltzmann constant. This formula can be written in this way. Now let's try to understand this. What is this PV? This PV is actually energy. If you calculate it dimensionally and you check the dimensions, you will see that this is the energy. So it means that, roughly speaking, this kBt is the energy per atom. And similarly, we can say that in Planck's formula, this kBt was energy of the photon. But how much this energy should be? And the answer is this energy should be the average of the energy available. So if we have energy over here and it goes to the average, the mean, and then comes down here, which means that all the energy available, the maximum of the photons will take that energy, and few of them will take that energy, and few of them will take that energy. That's why, if you remember the spectrum, black body spectrum, like this, that we had the average energy, that maximum of the photons took that energy, and few of the photons took that energy, and very few were that energy, the higher energy. So that's why when we have lower frequencies, we have few photons available here taking that energy, and when we go to the this maximum, here we have many photons taking the average of the energy, which is kBt. And when we go to the higher frequencies, you see that the probability of a photon taking this very high energy is very less, and that's why this curve appears to be in this range. So we see that by implying that the energy inside the black body, this radiant energy, is not continuous, but it comes out into the form of packets, solves the problem of black body radiation. This experimental observation, where this bell-shaped curve was not predictable from the Rayleigh-Jeans or other classical theories, quantum mechanics could predict that based on this assumption that energy radiated is in the form of packets. With this, I thank you, all of you, and if you have questions, I will be happy to answer them. Thank you very much.